Hello, welcome to another module in this massive open online course. So, we are looking at sampling, correct, and in particular we are looking at impulse train sampling to convert a continuous time analog signal to a discrete time signal, alright, where we are multiplying the signal xt by an impulse train, alright, and we have also derived an expression for the spectrum of the sampled signal in terms of the spectrum of the original signal. And what we have seen is the following thing. So, what we are doing is we are discussing sampling in particular. We have seen if x of t is the original signal, this is your continuous time analog signal which has spectrum x of omega, this is spectrum of the original signal. This is your spectrum of the original signal. The spectrum of the sampled signal, that is your x ts of omega, this is the spectrum of the sampled signal. That you can see is basically given as 1 over t as summation x omega minus k omega s. So, that is 1 over t s summation k equals minus infinity to infinity x of omega minus k omega s, that is basically shifted k omega s and adding for all k, that is adding for all shifts. And therefore, what we have seen is that if your original spectrum, let us say this is your original spectrum, if your original spectrum x of omega is given as follows. So, this is your x of omega, this is minus omega m, this is omega m, where omega m, remember this is the maximum frequency Now, if omega s is greater than or equal to omega m, now what happens is, now you see the sampled signal will have spectrum that looks as follows, that is it will have of course the original copy, that is, so this is scaled by 1 over t s, this is from minus omega m to omega m, and then you will have yet another copy that is shifted by omega s. So, this point here is omega s minus omega m. So, this is basically, and you will have several other copies. For instance, here you will have another copy that is shifted by minus omega s. Okay. So, these are basically all the copies, and then you will have again several other copies. So, these are your copies of the original. So, you can think of these as imposters, basically someone is who is trying to pass out. So, that is basically just not the original spectra, but copies of the original spectra. Someone is trying to imitate the original spectrum. Okay. So, basically what happens is, now when you have these copies and if there is no gap between the copies, that is omega s minus, so if there is a gap, correct, omega s minus omega m is greater than or equal to omega m, the maximum frequency, implies there is a guard band correct, there is a guard band between copies implies no interference or no distortion. That is, and this distortion is what is termed as aliasing. So, there is no aliasing, which means aliasing basically, an alias basically means an alternative name, correct. So, aliasing means basically some other frequency is trying to pose, right, with an alternative name, trying to pose as the original frequency. So, that does not happen. So, this spectral copy does not overlap with the original spectral band. So, there is no aliasing, there is some other copy is not superimposing itself on the original copy of the spectrum. So, in that sense there is no aliasing. If omega s is greater than or equal to omega s minus omega m is greater than or equal to omega m, the maximum frequency, which implies that omega s is greater than or equal to twice omega m, which is termed as the Nyquist frequency. Okay. So, this implies no aliasing if omega s greater than or equal to twice omega m and the sampling rate is greater than or equal to twice omega m. This is called basically the Nyquist criterion. On the other hand, if there is no guard, band, which happens, so this is your 1 over Ts, this is your omega m and this is your omega s minus omega m. In this case you can see there is overlap, which implies distortion when you sum them. So, on the other hand, when there is overlap, that is omega s minus omega m less than omega m, which implies omega s less than twice omega m, this implies there is aliasing, okay, which is equal to basically your, which is a form of distortion. So, what happens when omega, the sampling frequency omega is less than twice the maximum frequency, then we have distortion that is used that is arising because of the aliasing of these various spectral bands, the original spectral band and the copy of the same spectral band that is shifted by omegas, and for that matter also shifted by minus omegas. So, you will have aliasing in fact in every spectral band. So, again here you will have aliasing. Okay. So, because you have aliasing, you will not be able to recover the original spectrum, which brings us to the next topic that we are going to talk about, how to reconstruct the original message signal from the sampled signal. So, what we want to also look at now is the reconstruction of the original signal from the sampled signal. So, what we want to talk about is basically how to reconstruct the original, the reconstruction aspect. So, how to reconstruct the, by reconstruction we means basically retrieve, okay. Retrieve the original signal from the sample. So, how do you retrieve the original signal from the sample signal? Obviously, this is only possible when there is no distortion, correct? Okay. So, this reconstruction of the original signal from the sample signal, the exact reconstruction, we are talking about perfect reconstruction. So, the original signal is equal to the reconstruction or the reconstructed signal is equal to the original signal. This is only possible when there is no aliasing, all right. So, possible when there is no aliasing, okay. And when there is no aliasing, how we can do it is fairly simple. So, what we have over here is basically you have your copies of the spectrum which are not aliased. Remember, you can see there is a guard band, okay. So, this is 1 over Ts, which is simply a scaling factor. Now, I can in principle low pass filter this using an ideal low pass filter. I can low pass filter this using an ideal low pass filter such that I extract the spectral components corresponding to the original spectral. So, this is your ideal low pass filter, gain is unity. So, this is your omega m and the cutoff basically is omega c such that, and now look at this, this is your omega s minus omega m. So, this is basically your omega c, which is your cutoff of the ideal low pass filter, okay. This is your ideal low pass filter. I can choose omega c such that I can choose the cutoff frequency of the ideal low pass filter such that omega m less than or equal to, for that matter, omega c less than or equal to omega s minus omega m, okay. Only possible when there is a guard. Remember, for this to be possible, when omega s m less than omega m is less than or equal to omega s minus omega m, which means omega s is greater than or equal to, that is when there is a gap between those two bands, I can design a low pass filter, an ideal low pass filter such that it extracts only the original spectral band, original spectrum corresponding to corresponding to xt by appropriate suitable scaling, of course, while it suppresses, it cuts off the other copies, the other aliased, the other not aliased, the other copies, that is other shifted spectral copies of the original signal xt, okay. So, basically we want to multiply it by the ideal low pass filter, pass this signal, the sampled signal, through the ideal low pass filter. Omega c minus omega c, gain equals 1, omega c equals your cutoff frequency. So, pass this and to invert, to scale it back by the original amount, we can always choose this to be Ts. So, that we have 1 by Ts multiplied by Ts, that will give a scaling of 1, okay. So, you get back the original spectrum, okay. So, pass your sampled signal ideal LPF cutoff equals omega c, omega m less than equal to omega c less than equal to omega s minus omega m for reconstruction, okay. So, and when there is no aliasing, you can pass it through this ideal low pass filter, and what that will give you is, that will give you again original spectral copy, because when you pass it through the ideal low pass filter, the resulting spectrum of the output, the spectrum of the resulting output is simply the multiplication of the the spectra of the input, that is a sampled signal, with that of the low pass filter, which only extracts that original, which extracts only the original message spectrum in the band minus omega m to omega m, okay, because the cutoff frequency is greater than omega m. Okay. Now, without loss of generality, we can choose omega c equals omega m, that is, I can set the cutoff frequency omega s, omega c equals omega. So, I can choose, in fact, one possible choice is to choose omega c equal to omega m, so that you can be absolutely sure that you do not get any of the spurious spectral components of the sampled signal. So, I am choosing omega c, that is cutoff frequency equals maximum message frequency, okay, and gain is 1 over Ts, cutoff maximum cutoff frequency is the maximum frequency of the signal. Okay. Now, let us look at, now this is your low pass filter. So, let us call this spectrum as h of omega, correct. Now, h of omega equals 1 magnitude of omega less than or equal to omega c, or basically your omega m, zero otherwise. Now, what can we say about the corresponding impulse response h of t? Now, we know that if you look at the pulse in frequency of width 2 omega centered at 0, that has Fourier transform sin 80, and this we have derived before. This has Fourier transform sin 80 divided by pi t. What is this? This is basically your, if you remember, this is basically your pulse of width 2a centered at 0, that is from, and height 1, okay, minus a to a. Okay. So, this is your Pa2. So, that has the impulse response sin 80 by pi t. Now, this implies that if you consider the pulse of width 2 omega m centered at 0 omega, that has impulse response sin omega m t divided by omega divided by pi t, I am sorry, divided by pi t, which implies, now if you multiply this by Ts, Ts is, remember, nothing but a scaling factor. So, Ts into P of 2 omega m omega, that is basically, this is your h of omega. This has the impulse response sin Ts. So, you multiply on the left by Ts, you multiply on the right also by Ts. Okay. So, since the Fourier transform is linear. Okay. So, this is sin omega m t divided by pi t. Okay. So, that is basically your impulse response of the ideal LPF required for reconstruction. This is the impulse response of your ideal LPF. So, pass the signal. So, you pass XST through ideal LPF. Okay. So, ideal, you pass it through the ideal low pass filter. Basically, we cut off frequency given by omega m, and gain is Ts, all right, to invert the factor 1 over Ts, all right. So, Ts multiplied by 1 over Ts gives an overall net gain of unity or 1, okay. And therefore, now when you pass it, so let us denote the reconstructed signal by x r of t, remember this is your sampled signal xst times h of t. So, this is basically your reconstructed signal. Okay. This is which is equal to summation k equals minus infinity to infinity x of k T s delta t minus k T s convolved with sine of omega m t divided by pi t into T s. Now, of course, you can also note that we can also choose the sampling frequency equals twice the Mach, that is the Nyquist rate, alright. The sampling frequency equal to twice omega m, which implies 2 pi by T s, that is if you choose 2 pi by T s is equal to twice omega m, which means omega m equals pi over T s. Okay. So, which means pi over T s is omega m. So, you have pi, this factor pi over T s, which basically reduces to omega m. That is when you choose the sampling frequency omega s such that it is exactly the minimum sampling frequency that is required to avoid distortion, that is omega s equals twice omega m. In this case, we have omega m equals pi over T s, where T s is the sampling duration or the sampling interval, the interval between two consecutive samples. Okay. And in this case, what we have is x, the reconstructed signal is summation k equals minus infinity to infinity x of k T s delta t minus k T s convolved with sine of omega m t divided by omega m t, which is basically, now again simplifying this, summation k equals minus infinity to infinity x of k T s. Now, remember you can take the sine, the sinc function inside. So, the sine of omega m t divided by omega m t convolved with delta t minus k T s, that gives me sine of omega m t minus k T s. That is basically shifting it to k T s. So, this is your reconstructed signal. And you can see this basically interpolated, this basically taking the samples and interpolating them. You are performing linear combinations of these samples x k T s by interpolating them by a sinc filter, alright. So, you are basically interpolating the samples using a sinc function in the time domain. Okay. So, interpolation using using a sinc in time domain, or basically a sinc filter. And further you can simplify it by noting the following thing. You can also write it, Now, of course, you can realize that XR of t, this reconstructed signal, is equal to the original signal only if there is no aliasing, correct. Only if no aliasing. This implies that omega s is greater than or equal to twice omega m. And you can also further simplify this as summation k equals minus infinity to infinity x of k T s. Remember, we have omega m equals pi over T s, which means omega m into T s is equal to pi. So, this will be sine of omega m into t, sine of omega m into t minus k omega m into T s minus k pi. So, divided by omega m into t minus k pi, omega m T s equal to pi, correct. So, that is basically your expression for the reconstructed signal. Okay. So, this is basically your again the reconstructed signal in time. This is the reconstructed signal from the sample signal, and perfect reconstruction is possible, of course, when there is no aliasing. All right. So, you sample it at a sampling rate that is greater than or equal to Nyquist rate, then pass it through an ideal low pass filter which satisfies the given cutoff frequency requirements, and basically based from from that you can reconstruct the original signal by extracting the spectrum copy and extracting the spectrum corresponding to the original signal and suppressing all the spectral copies, correct, or the aliases that arise because of the sampling process. And this is only possible when there is no aliasing, when there is no distortion that arises due to aliasing, or the sampling frequency is basically greater than the Nyquist rate, that is twice the maximum frequency of the signal. All right. So, that completes our discussion of the sampling as well as the reconstruction process, which, as we have said, is one of the fundamental aspects of signal processing and communication, since most of the processing is digital. So, we would like to take while the naturally occurring signals are analog. So, one would like to process or convert. The first step in the storage and transmission or of signals is usually acquiring the analog signal and converting it into a digital signal, and the first step is sampling, converting continuous time signal into a discrete time signal. All right. So, I will stop here and continue with other aspects in the subsequent modules. Thank you very much.